in late 1979, they got money, both Caltech and MIT, and by 1983, the new proposal came in. Ray had recognized he had fallen behind. He'd gotten this grant and got the proposal. They put the proposal in. I had seen an early draft, an intermediate draft, and they were saying it was 30 million. When the proposal finally went in, it was 100 million, which is a really significant amount of money in those days, to build the two instruments in the United States, right? And in 1984, they did get the funding, right? And in 1992, started 1992, the font didn't go right. And so in 1984, they got the funding. In 1992, they started it. The fighting was so bad that Barry Barish was called in to become PI, and then a couple of years later, he also became director because he divided the project into the science team and the project team, and ran the project team the way an engineering group would do it. And so it became very important to the success. And he led the collaboration success. The first operation was in 2002 to 2010. Then they shut off for 5 years, 2010 to late 2015, in which to make the engineering upgrades. And as I said, during the engineering turn-on, they turned Advanced LIGO in late 2015. They saw that the total cost by the time they got there is $600 million. Right? So it's really a substantial amount of money to find something that Einstein first thought was too weak to discover and probably didn't exist anyway until finally he agreed it did exist. Okay, so here's pictures of the two observatories. I'll talk about them in a little bit more detail. But you'll notice they're in a place that's big and flat. And the reason is you have to make these big, and you need land, and you need a lot of other stuff. And you see they're 3,000 kilometers apart. That isn't going to work either. Let's see.
A laser beam is split and sent down a pair of long perpendicular tubes, each precisely the same length. The two beams bounce off mirrors and recombine back at the base. The light waves come back lined up in such a way that they cancel each other out.
And you add them together, you get nothing. You get a zero, a big fat zero. No light gets detected at the photodetector.
Do you believe he's a professor?
But when a gravity wave comes along, it distorts space and changes the distance between the mirrors. One arm becomes a little longer, the other a little shorter. An instant later, they switch. This back and forth stretching and squeezing happens over and over until the wave has passed. As the distances change, so does the alignment between the peaks and valleys of the two returning light waves, and the light waves no longer cancel each other out when added together in the recombined beam. Now some light does reach the detector, with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
Okay, sounds easy, right? Okay. Well, and besides, you saw the Earth do this thing, even though the sign said there. If you look, the small print said, effect is greatly exaggerated. The effect is greatly exaggerated. The amount of distortion for the whole length of LIGO is 1/1000th of the size of a nucleus. And we're measuring this with light, which is in the size of an atom. So it's measuring us to very precise. So it's an engineering marvel. So I assume that with that Nautical Institute, people will really be interested in this. So here's what the laser system looks like for real. It's a 125 watt laser, which is it's picked for various reasons. It goes into a mode cleaner. So if I have my laser here, well, you can't see it. I can barely see it. Whoops. Now that's terrible. So if I shine the laser on the wall, you see it has speckles. Those speckles are caused by the fact that there are more than one mode of laser light going on in there. They interfere with each other. And so there's a mode cleaner and also a period where another place where more energy is stored when you go from 125 watts up to about 6 kilowatts, right? I can't read it, so it's easy. And then eventually you go into the laser itself, And there again, the light is stored. It's bounced back and forth a few hundred times so that you're almost up to a megawatt of power being stored in the laser. And so there are mode cleaners when you come out and recycling mirrors. There's a lot of stuff done to make it so this laser interferometer is a very precise microscope for measuring smile changes in distance. So then I have another video.
In an interferometer, a laser beam is split into two beams. Mirrors reflect the beams, so they meet again at a starting point. If now the distance to each mirror is exactly the same, no light will be seen by the detector. The waves of one beam extinguish those of the other beam. This is called interference. A passing gravitational wave distorts space, making one arm slightly shorter and the other arm a little longer. The light waves do not cancel each other anymore, and we now measure a tiny signal in the detector. Now we add an extra mirror in both beams. In this configuration, the beams bounce hundreds of times back and forth between two mirrors, before returning to the beam splitter. The intensity of the light in these so-called Fabry-Perot cavities increases substantially. The cavities boost the interference effect a few hundred times. The sensitivity is further increased with two additional mirrors, which recycle the outgoing light into the cavities, and with a so-called mode cleaner, which removes disturbing noise from the laser beam. The light power in the cavities is increased to hundreds of kilowatts. Even more complex optics and electronics are required in order to keep the mirrors properly aligned and in position. Ground vibrations at most about 100 nanometers are nevertheless millions of times greater than the vibration caused by a gravitational wave. Therefore, all components are mounted on horizontal and vertical vibration attenuators, the best in the world. While the ground is trembling, the mirrors and beams feel nothing of it, thanks to the super attenuators.
It's getting a little more complicated.
Also, air presents a problem. It gives rise to unwanted vibrations, such as due to sound. Four so-called cryogenic traps provide an ultra-high vacuum quality. We can pick up hundreds of times more signal of a gravitational wave by extending the Fabry-Perot cavities to 3 kilometers. This and much more is needed to realize an interferometer for detection of gravitational waves.
So what I'm trying to show you with this video is that it's actually very substantial engineering project, right? In order to measure the gravity waves, the engineering things that you have to overcome are incredibly large, and you just saw a portion of them. If I have time at the end, I'll show you a few more examples of what has to be done, why it took them, a few years of operation, and then 5 years to make the upgrades, and then there was a downtime recently, and then another upgrade before this new set of measurements. And each time, engineering is done to clean up and simplify, make things better. Okay, so again, this is supposed to be full screen, but it didn't quite come out that way. Here are the black holes superimposed upon a curve where you see space-time, you see the direction in which test particles will go, but you'll see the potential well, that is the curvature of space-time, and you see the black holes coming together by radiating away energy, and you see the potentials will get closer and closer together. And as we get closer, we'll slow down a little bit. And you will see black holes. Generally, when you study black holes, we only teach you about static black holes or simple rotating black holes. But when you get into close black holes, you will find there's more than one horizon. You will see it when these get close, that their apparent horizons touch first before their event horizons touch. Now, for those of you who are going to do quantum computing and information theory, that's very important. For everybody else, we don't care. It's all over, right? But someday we're going to have quantum computers, and someday isn't very far away. Someday it's within 5 years. We're going to have a lot of quantum computers around, and the information that's involved is going to become important. And so one of the hopes that this is not only going to learn about general relativity and about astronomy, we're going to learn something about information theory that will help us to do that. I see we have another thing. So here's the data again, and it's the data superimposed on each other and superimposed on numerical relativity measurement estimate of what was going on. So let me go on to the next one. So here are the raw data, right, in both cases, and then the raw data flipped over and shifted so that they line up with each other so you can see how they compare versus the reconstructed numerical relativity kind of thing. Do I need to, is that a mascot? But, okay, so this is a tremendous signal and amount of data, and yet, had this been light, we'd all been blinded, right? It would have been so bright, it would have been like the sun was up. Okay, so now the fact that true detectors becomes important. You can measure the time delay by comparing the two signals and seeing when they line up. That tells you what the time delay is. If you have two objects and you have a time delay, a fixed time delay, there's a circle on the sky which fits that. And then there's the sensitivity. The gravity wave detector is sensitive when the gravity wave stretches in one direction, but when both are stretched equally, it doesn't see. So is the responsivity, and so you could tell that this event came from that part of the circle around the sky. Right? And with only two detectors, you can see only that much. We'll see what happens when you add a third detector. And at the same time of this first event, there was a reported gamma ray event by the Fermi satellite, and that was thought to come from somewhere in that region. And this is such that the probability was very low, and people speculated about it. There was a lot of speculation. Was there some light that came from this event or not? And if it was pure black holes, there's no reason to expect there should be light unless there's some material around the black holes. And so there was a big debate about this, but that died out over time. And so they're the two who are laughing. So the question was at that point, what next? Well, LIGO and Hanford had been upgraded. There was, as a result of having to review Ray Weiss's proposal, the building by the Germans, building of GEO 600 in Germany, and then the French-Italian group build near Pisa in Italy, the Virgo detector. And the Virgo detector had been running, and it was upgraded, but it was running slower and behind, and it wasn't on for this great event that came through. It came later. But immediately, LIGO and India signed an agreement to build another detector in India, and the Japanese are building a super-duper underground superconducting, system which should be on the air in 2 or 3 more years. So that's where the ground-based kind of detectors were going. And so here's the sort of the history. In the center is the little red sphere, which represents the range out to which the original LIGO could make detection. Then advanced LIGO came on, and it went out to this yellow sphere, which was 27 times the volume. So you expect the rates to go up a factor of 27. And then there are plans to upgrade till you get out to this next spherical volume, which is about another factor of 30. So at the early time, I was estimating, okay, well, we're seeing one event in such and such a time. They should be eventually seeing 27, 30 times as much as that when the full upgrade is done. So you can predict what's going to happen in the future, sort of, but you don't know until things happen, right? So I was getting ready to give a talk at the request of the Nobel Committee, and the second event came out, and this cartoon came out at the same, just before the event came out, which was very good timing. These are all these gravity wave astronomers, you can tell because they have a telescope, but they're in there looking at the screen, and they're saying, oh, black holes, and there's a guy in the background pounding on the wall, right? But it turns out that wasn't the case. There really was another gravity wave event that came out.
Black holes performed a
this is 1.4 billion light years away.
They spun around one another, coming closer.
So it happened
and closer
1.4 billion light years ago.
Finally, they collided.
Right? So they could do the
This
same
dance
animation,
created
right?
ripples in the fabric of space and
At least you see
time,
it full scale
also
this
known
time.
as gravitational waves.
So there's
In
a ripple
December
going
of
on,
2015,
but you only see
those
the really high
gravitational
frequency
waves reached Earth and were detected
See,
by an instrument
effect is
known as the
exaggerated.
Laser Interferometer Gravitational Wave Observatory, or LIGO for short. Scientists with LIGO announced the detection of the two black holes on June 15th.
Again, it's the chirp, but it's a different frequency. This is a higher frequency. Means
This
they're
is
lower
only the
mass.
second time that scientists have ever directly detected gravitational waves. The first detection, also made by LIGO, was announced earlier this year.
Lower frequency.
Currently, all other telescopes and space observatories study the cosmos by collecting light or other particles. But the black holes detected by LIGO are not expected to radiate light. So by looking for gravitational waves, LIGO is illuminating otherwise invisible sectors of the
This is
universe.
an ad for LIGO. Okay. All right. So here it's different. You will notice this goes on for almost a whole second, right? And you see many more orbits before it chirps, and you can look at the various phases of what goes on, and the fact that it's 14 solar masses and 7.5 solar masses instead of 36 and 29. The total is almost 21 solar masses. Again, it puts out, on the scale of solar mass, 1.5 solar masses of gravity waves. This one, there's evidence that at least one of the black holes had significant spin, which is an interesting phenomenon if you care about these kinds of things. And again, it gets up to better than half the speed of light before they touch. Okay, so now it turns out there was a possible detection, which they didn't release. And if you look, the first detection, you can see the frequency and the amplitude mean there were higher masses and it was closer. There was a possible detection, and then there was this new second event that was confirmed. And the second event meets the sufficient criteria that you got it right. And so you look through 36, 29, 23, 13, 14, 7.5, right? And in gravity waves, you get 3, 1.5, and 1 solar mass's worth of energy. These are really energetic events, and they're barely detectable. That's the scary thing, right? Okay. So I have more details on these in case you're interested in it, but let's... apparently I got ahead. So how do we know what we saw? Well, it's just, you do the math. That's the problem. Science requires you to do math. So you do the best fit for the gravity wave detection, and you see what kind of frequency you get for the strain and whatever else you get, and you do it for both events, and you say, this is how I determine these parameters. I can compare that to what my theoretical model is for binary star in spiral. You notice it's much higher frequency, right? And it goes on for longer. And you can compare that, and you realize these are really black holes and not neutron stars. We're going to turn this around later. When we see the neutron star, it's neutron stars, right? So it's not black holes. Okay, so here's LIGO. LIGO's first observing run originally was supposed to start after that first event, but they extended the starting run to just before that first event. the possible event and the other one. So you can see the rate at which they were finding them. They found, one in September, a candidate in October, and then just the day after Christmas, they found another true event. So that's a pretty good rate, especially if you think you're going to get the 30 times that in the future if you upgrade. But it tells you that that the thing is finally working and it's doing well, and it's good to go on with these observations. And you can also look to see where they come from. So here are the two events and the candidate event, and you can see roughly what parts of the sky they come from. It's pretty boring because they cover such a large fraction of the sky. If you had the Virgo event along with LIGO, you would have been able to concentrate it down to that level. Right? That's the prediction that was done at the time. So that's the reason people were upset that the Virgo instrument was a year behind schedule and not getting turned on. And so now, on the September 17th, so just about a month ago, there was a new event released. There's a new event, and you can see the chirp patterns, and it was seen by Hanford Livingston. That they had been turned off for a while to do the upgrade. The upgrade had worked. They'd been able to improve the laser at Livingston, but they weren't able to make the thing stable and work at Hanford, and they went back. So you see the sensitivity at Livingston is now better than the sensitivity at Hanford until the next shutdown, and they can get that fixed. But you'll see Virgo wasn't as good, but there's a signal there that you can see. Right? That you have to sort of, if it wasn't in coincidence, you wouldn't necessarily believe it. So here is the Virgo Observatory. It's in Pisa, and it's in the farm area, so you can see the farm fields. I have a picture when the fields are cleared and then when they've planted it again, and the irrigation waterway. But this is what the detector looks like. It's very similar to the others, but there are mountains off on that side. Okay, so the Virgo, this is really the introduction of Virgo into the thing to show that by having that third detector, you're able to get the localization much better. And that turns out to be actually important for the next events. So it gains you about a factor of 10 in what fraction of the sky you're looking at by having that third detector. And so you see it down here in the bottom left, the extra events compared to the previous events. Okay, and now we're starting to pick up a list of our favorite black holes out in space. There are still black holes that we know in binary pairs or other pairs from X-ray studies, and we know their masses. And then we have the black holes we think we've learned from the gravitational waves. And one of the differences... Is one of these working? Okay. Well, it's partly my fault. I'm jet lagged. I'm not staying fixed, and I move too close to the speakers. But the one of the things that we worry about is, are these the right sources of black holes out there? We hadn't known very well what the inventory of black holes are and what the situation is and what the prediction is. It's actually hard to make big black holes. If you have a supernova and you try to explode the supernova and get that material out to make the next generation of stars, galaxies, and planets, if you make a really big black hole in the middle, it just sucks everything back in and you don't get it. And so we didn't know what the situation is and how they evolve. And this is, we're starting to build up the inventory on this. And then the question is, were these primordial black holes, which would tell us something different about the early universe, or were these stellar remnant black holes? And so that's part of the things we're learning from this. Okay, so here's some artist pictures of black holes, just because, black holes are pretty boring. So what you'll see is black holes are really great if you're a scientist, because they're really simple. They're just these holes, right? I mean, they're just the two black holes merged together. It's really simple, straightforward calculation. It's hard math, but it's a calculation straightforward. Two neutron stars, I'll show you pictures of. They are messy. They're engineering nightmare, but we'll see. But so here were the events that we're talking about in the time scale that were observable by these various detectors. Okay, and this is how far out they were going. And this is the thing that tells you a little bit about the engineering problems. Okay, so this is the frequency at which you're observing, and this is the strain noise in the detector. That is, you just see how much the laser interferometer output is varying, and you do the Fourier transform or the power at each frequency, and you look and see, and what you see is what mechanical engineers dread. That is, huge number of resonances, right? Because you've got all these mirrors, these towers, all this kind of stuff, and the mirror is vibrating because it's being supported, it's vibrating because of thermal noise, it's vibrating for lots of other things. So you get resonances and lots of things, and the thing is swinging, the face is vibrating. So the whole experiment is to put this up, measure these things, and figure ways to damp these resonances out till eventually you can get down towards those blue curves. That's why it takes so long. You have to get in there, build the detector, find out what the resonances are, find out ways to damp these resonances out. And that's what the whole improvement is about. And you can see what this ultimate one is. Eventually, you get to the point where you're limited by the Heisenberg uncertainty principle. That is, you're trying to measure the length of these two arms. That is, you have to know the positions of the mirrors, and you know that the error in the position and the error in the momentum of the mirror is greater than h bar, right? And so you tune the laser in such a way that the seismic noise of the Earth and the noise from the low frequency noise from the laser are pretty much matched, and you do that. And in the early days, we knew that neutron star pairs existed, and there would be such a signal, and we knew what frequency they should be in, which is around the 100 to 500 hertz. And so LIGO was designed to have the best sensitivity there. Nobody thought that there were a lot of 30 solar mass black hole binary pairs out there to be discovered. They show up at a slightly lower frequency. So this is an example. Here's an example of how well they have done. So Hanford is in red. The improvement didn't quite work to get the higher power laser the way it did for Livingston. So you can see Livingston is better at the low frequency noise. It's improved so it can see the big black holes better. And you can see in purple the Virgo, right? Virgo has only been in the air for a short time. It hasn't had the second shutdown to try and get rid of all these resonances and tunes. So if you're an engineer, this is your nightmare, that you have to get rid of every resonance in your system, right? And this is a big, complicated system. Right? Okay, so let's talk about, before I go on to the final event, because it'll get sort of interesting, let's talk about what we think should be going on in gravity wave astronomy. And I've been talking about the ground-based interferometers, and that's measuring stuff at the frequency of around 100 hertz. Right? As I say, the neutron stars are 100 hertz to 500 hertz during their chirp, right? And there has been a long time a proposal for a space-based laser interferometer. In fact, that's one of the reason that Kip Thorne and Ray Weiss met was they went to a meeting that NASA was holding asking for new ideas what to do in space. And Ray was convinced that doing this whole experiment in space was the right way to do it. Well, that will probably happen in about 10 years from now that gravity waves have been discovered. But another thing that we can do is we can use the fact that we have these pulsars, which are incredibly good clocks, to be the equivalent by having all these clocks positioned far out in space. When a very long wavelength gravity waves go by, it changes the distance and therefore changes the arrival time of the pulses, and you can measure that. So if you find some very stable pulsars and time them, you can look for gravity waves. But you're looking for gravity waves at a much lower frequency. And then you can do my favorite thing, or not my favorite thing, what I've been doing most of the time, use the relic radiation from the Big Bang, the cosmic microwave background, and look to see the effect of gravity waves. The gravity waves are a quadrupole field. They stretch in one direction and compress in the other direction. If you do that, that will couple very much to Thomson scattering, which happens to have a quadrupole cross-section, and cause polarization of the radiation. And you'll get these complicated patterns. And we thought, we had a report a couple years ago from the BICEP 2 group that they had discovered the pattern that you'd expect from gravity waves. But unfortunately, it turns out probably to be a pattern from dust and the magnetic fields in our galaxy, because you get the same pattern from magnetic fields as you get from the gravity waves. And so, but we're waiting to see. But those are the ranges over which you look, and those are interesting because they tell you about different epochs in the universe. So from the Big Bang, there's tremendous amount of energies and energy flowing around, and so you can get gravity waves from all different ranges. You get them from fluctuations in the structure of space-time itself. You can get it from phase transitions and from symmetry breaking and so forth. So there's a huge number of things that can go, and some of them become very interesting. And so you can look at it and see what science are you doing with each of these detectors. With the cosmic microwave background, you're looking at the universe as a whole and trying to see what happened early in the Big Bang. But with the pulsar timing, you're looking at supermassive black holes. We know in the center of every galaxy there is a black hole whose mass is somewhere between 10 to the 6th and 10 to the 8th solar masses. That is 1 million to 100 million solar masses, and they're huge black holes. I mean, it's scary, right? Don't drive through the center, right? Stay out of town, right? And there, the space-based interferometer should see the compact binaries in spiral, and likewise, the very compact, the pulsars, the supernova, the other kinds of things you will see with the terrestrial interferometers. The terrestrial interferometers, it took 40 years to get, but you could start building them way before you could start building big things in space. So that's why they're ahead. Okay. So one of the things that was interesting that was realized immediately with that first event, because nobody thought there were 30 solar mass black hole pairs going around, is that if you had the laser interferometer in space, LISA, and you started observing, you would see 30 solar mass black holes for about 10 years and be able to measure their position, because as you orbit around the Earth, or the sun with the Earth, you can get some directionality out of it, and you can then predict when it's going to coalesce and roughly where it's going to coalesce, and you can tell people to look there and when to be looking there and when to have your detectors on in order to see it. And so it's perfect for advanced LIGO, Virgo, and for the new generation of stuff that you could detect these and see that. And so in less than a decade, when we have the laser interferometer in space, we'll be having people making predictions about when there will be detections, and people will be able to follow up them a great more. But by that time, the many of the other things will be done. But the LISA is actually designed to see what happens when two galaxies merge. Eventually, the two black holes get in close to each other and spiral and merge. And it will see those, and it will see anything in the invisible universe is visible to LISA. The signal is, if you have 10 of a million to 10 million solar mass black holes merging, the strain is so huge you can see it across the entire visible universe. You just need the time for it to arrive. Okay, and so here's predictions about what things will go on, and you'll see these have similar shapes. They're all kind of uncertainty sensible shapes, except when you get to the pulsar timing, because then it's experimental lifetime shapes. It's cut off sharply on the left because you don't want to observe for 10 years. It takes you a while to do that. And so there's astrophysical implications, as I showed you the plot before, of the known black holes plus the new known black holes. So that's something we're studying and finding more interesting. There are tests of general relativity. You can test general relativity. People have been worried about general relativity failing or not failing. So there is, that blotch in the back is the galaxy in which this happened. It's a dwarf galaxy, but this happens to be now a metal-rich dwarf galaxy, great for mining. And I think I had a couple more slides. Okay, so this is just to show you the chirp and the gamma rays that come, their timing. And one of the big questions is, why does it take 1.4 seconds from the merging of the neutron stars till you get the gamma ray burst? And generally, we think the gamma ray burst requires starting up the central engine, which makes the relativistic jets in order to come out. But the kind of time scale that should be is sort of more like a half a second, but when you do rough calculations, but I haven't done that before. I haven't made one of these before, so I don't know. I can do a rough calculation, we see. But in fact, it took about 1.74 seconds. And so part of the question is, what does that tell us about the equation of state of nuclear matter, right? So the fate of the binary neutron star is that it can be a stable neutron star, but if it's over a certain mass, it's going to collapse because it's cheaper energetically to be in the black hole than it is to try and maintain as a neutron star. But you can make a supermassive neutron star that's supported by its rotation and by a stiff equation of state, and it will last for a little while before it tunnels to become a black hole, right? It's quantum mechanics on a huge scale, right? And it's also then doesn't matter, it's the central engine from what's going on. So these are the questions we have, and so I was getting the sign that I'm overrun. You know, binary neutron star mergers are much messier. The simulations look much prettier looking, but, you know, Einstein was still right. So I'll stop at this point if there's any time for questions. They made me it's her fault. She made me turn my phone off, so I didn't know what time it was. But I know I was running late.